Um, so my name's Alden. I have question 8, and this is from November 2009, paper 2, and this is question 8, C and D. So the question reads as it follows. The following diagram shows a circle with center O and radius 4 centimeters. I recreated the diagram that's given in on the paper on the question, and reproduced it here in this question. And so there's some information that's given at first is the points A, B, and C lie on the circle. The point D is outside the circle along OC, and angle ADC is equal to 0.3 radians, and angle AOC is equal to 0.8 radians. So question C asks, find the area of sector OABC, and question D asks, find the area of region ABCD. So that should say area, not R. So for question C, I've just kind of simply outlined what we're trying to find here, and I've kind of highlighted that with the red scribbles. So we're trying to find that area of OABC, which is just right here. So just basic information that we need to know first is that 180 degrees is equal to pi radians, and 180 degrees divided by pi is equal to 1 radian. So also what we need to know is that in radians, the entire circle is 2 pi. And since we're given that this right here is 0.8 pi, 0.8 radians, sorry, to find the fraction of this angle compared to the entire circle, we just need to do 0.8 radians divided by 2 pi radians, which gives us 0.127. So simply to find the area of the circle first, we can find pi r squared. Since we know that the radius is 4, we can just plug 4 in for r, and you get 16 pi. Or if you just multiply it so you get a number value, you get 50.27 centimeters squared. The area of the sector now, OABC, since we know what the fraction is of 0.8 radians over 2 pi, we use that value, so we use 0.127, we multiply that by 50.27 centimeters squared. And that way we get 0.127, that fraction of 50.27 centimeters squared, and so the area of the sector OABC is equal to 6.38 centimeters squared. So that's part C. And moving on to part D. Similarly, I just kind of highlighted what we need to find with the green scribbles. So I've kind of recreated this triangle right here without the circle, so it's just easier to see this kind of information. So what we need to find first is find the angles of DAO, so that's this angle right here, and ACD, which is this angle right here, which we know is 90 degrees because this is perpendicular to this line. So starting off, we know that angle A is equal to pi, which is 180 degrees, but in radians. So it's pi minus D minus O. We know that D is 0.3 radians and that O is 0.8 radians. So when we do that pi minus 0.3 minus 0.8, we find that A is equal to 2.04 radians. To find C, we know that this is 90 degrees, and we know that from the previous question, just some basic information is that 180 degrees is equal to pi radians. So when we divide pi radians by 2, we find that that is the same, that's what 90 degrees is in radians, which is 1.57 radians, which we have here. So using the sine law, which is sine A over A equals sine B over B, which is equal to sine B over B, we can use sine law to find the length of AD and the length of DO. So first, using sine A over DO, so sine A over DO is equal to sine D over AO, sine D over AO. We know what angle A is, we know what angle D is, we know the length of AO because this is just the radius of the circle here. So we know that that's 4 centimeters. So since there's one unknown, we isolate it, and when we isolate it, we get DO is equal to 4 sine 2.04 over sine 0.3, and after that, after putting that in our calculators, we find that the length of DO is 12.07 centimeters. Now we do the same to find what the length of AD is, and so we still use the same values for sine D and AO, which is 0.3 radians for the angle and 4 centimeters for the length. So now instead of trying to find DO, we find AD. So we put in the angle of O, which is 0.8. Do the same process, and we find that AD is equal to 9.71 centimeters. This is the first part of trying to find the area of this region right here of ABCD, and so now we move on to the second part. So this is just the second part of this question, and I kind of recreated these images right here to just so it's a visual aid for us. So since we know AD from just doing this right now, we can now find AC using the sine law yet again. So if we do sine C over AD equals sine D over AC, we just plug in the values that we already know, that we've calculated, and except this time, so for sine C, we plug in 1.57 for that angle, and the length of AD is obviously 12.07, sine 0.3, because that's the angle, and we're trying to find AC, which is the horizontal value of this, which is AC, which is also known as the height of the triangle. So when we kind of calculate it, we rearrange it so that we isolate AC. We find that the height, or AC, is 3.57 centimeters. So in doing, the reason why we're finding the height of the triangle is so that we can find the area of this triangle. We already know what the length of the base is. So when we know the height, then we simply just use base times height divided by 2. So by doing that, we get 12.07, which is length of DO, times AC, which is 3.57. Divide that by 2, and we get 21.54 centimeters squared. So now we know the area of the triangle, which is 21.54 centimeters squared, and we know what the area of that sector OABC is from part C. So to find the area of ABCD, we just need to subtract OABC from OAD, or ADO, which is the triangle. So basically, since we know what the area of the sector is of OABC and the area of the triangle, we subtract the area of sector from the triangle, which is 21.54 centimeters squared minus 6.38 centimeters squared. And for a final value of ABCD for that sector, we get 15.16 centimeters squared. And that is how you do part C and D.